So we can look at the process of a solute dissolving as an equilibrium process. We looked at this with evaporation. So initially you've got, say, your solid sodium chloride sitting in the water, and initially you've got dissolving happening and no recrystallizing because there's nothing dissolved to recrystallize yet. So we've got sodium chloride down here, the solid, and it's going to separate into the ions and go off into solution. But the ions can also come back together and recrystallize and reform the solid. Initially, the rate of dissolving is much higher, and the rate of recrystallizing is much less. But as the situation goes on, we establish a dynamic equilibrium where the rate of dissolving and recrystallizing is equal. So here we have pictures. So there's our salt crystal. There's no dissolved sodium and chloride ions, so we can't have any recrystallization. We just have this dissolving. As this begins to dissolve, now the concentration of chloride and sodium ions that are in the solution is going to increase. And as that increases, then the rate of recrystallization can increase. The rate of dissolution will remain the same. The rate of recrystallization increases until they become equal. Then you have a dynamic equilibrium. So if you have a saturated solution of table salt in water and you let it sit covered so that you don't lose the water, but you just let it sit for a long period of time, you come back and you'll notice the crystals are bigger than they were before. The amount of crystals are the same, but they've changed shape. And that's because this is also like sublimation in the freezer. You have things leaving and things coming back, things leaving and things coming back. And so the shape can change. Actually, before we get to this, when we digested our calcium oxalate in our in that lab that we did, 4K, remember with the Gooch crucibles, and you had the beakers, and we boiled them for a long time until the solution changed color. What we're allowing there is dissolving and recrystallizing to happen over and over again. And that gives us larger crystals and more pure crystals because as they recrystallize slowly, the lattice tends to reject impurities. When you form a precipitate very quickly, it can trap impurities. When you allow it to digest, to dissolve and recrystallize, those impurities get excluded. You get larger crystals which filter better, and you get crystals that are more pure. So, in a saturated solution, the dissolved solute is in dynamic equilibrium with the solid solute. So the solution is essentially full. We can't have any more dissolve. If we put more solid in, it won't dissolve. It'll just sink to the bottom. And it will participate in the dissolving and recrystallizing process, but we're not going to dissolve anymore. That's a saturated solution. It's full. An unsaturated solution contains less than the equilibrium amount of solute. So all of the solute dissolved. If we put more solute in, it will dissolve also. And you can keep adding solute until you get a saturated solution. And what's very strange is you can also have a supersaturated solution, which contains more than the equilibrium amount of solute. These solutions are unstable, and they tend to spontaneously recrystallize to precipitate. So the way you can make a supersaturated solution, solubility depends on the temperature. And so at a higher temperature, the substance is more soluble. So you heat it up, and you can get all of it to dissolve. And then if you cool it down carefully, you can fool it. You can fool the solution. And you can get it to be more concentrated than it should be. This is similar to what we did when we did the melting point of the sodium, I think it was sodium thiosulfate. Remember those crystals? And you melted them, and then you put them in ice water, and you cooled it down, and then you dropped a seed crystal in there, and the temperature went up. It was crazy, huh? Well, if you think about it, it's crazy. Otherwise, it's just weird. So what happens here, this is a solution of sodium acetate that's supersaturated. And so when we disturb that solution, we cause precipitation to begin, and as soon as it begins, it just goes very, very rapidly. This reminds me of cartoons, especially like Bugs Bunny and Roadrunner, where they were always running off of cliffs, right? They'd run off the cliff, and instead of just falling with the first step off the cliff, like normal physics says should happen, they didn't fall until they noticed that they had run out of land, right? So this is a little bit like Roadrunner or Bugs Bunny or whoever in midair. And when you disturb it, it's like saying, hey, you're not standing on anything. And then he's like, ah, and then he starts to fall, right? So that's kind of what this is. So I've got a couple of YouTube videos here. I think I have a couple of YouTube videos. There we go. So this is a supersaturated sodium acetate solution. I just stuck a spatula in there. Isn't that cool?
Yeah. Temperature be hot?
Yes. As it crystallizes, it gets warm. This is another one. It's sometimes called hot ice. So here they're just having some fun with it. So they've got a bunch of supersaturated solutions. You see the temperature goes up 52 degrees. That's a lot higher than room temperature. And it's mostly solid now because it was so supersaturated. There's some liquid in there, but so that's a supersaturated solution in the beaker, and then as they pour it out, that disturbs it and it crystallizes, so you can make these cool sandcastles. Except they're not sand. And they're letting it touch the solution in the beaker, and then the crystallization just travels into the beaker. The sodium acetate needs a nucleation site, a place for the crystal formation to begin. And once that begins, it just goes really fast.
In this series.
No, we don't want to hear about that. So the solubility of most solids increases with temperature. Sodium acetate isn't on here, but there's some other compounds like potassium nitrate. And solubility here is given as how many grams of the solute will dissolve in 100 grams of water. So at freezing point, it's just maybe 13 grams. And as you heat it up, the solubility increases dramatically. So up around 40 degrees, now we've got over 60 grams will dissolve. And sodium acetate has a similar curve where the solubility increases dramatically. For sodium chloride, there's very little difference in how much will dissolve with temperature. And then there's sodium sulfate is unusual in that at a higher temperature, it's less soluble than at low temperature. There are substances like that. So recrystallization, I kind of already talked about this. Technique used to purify a solid. This is a picture of rock candy. Rock candy is formed by recrystallizing table sugar. And if you want to try that at home, you certainly can do that. Make sure you look up some instructions, though, because if you don't get the solution concentrated enough, it's not going to work. I tried it once as a kid, and it was a miserable failure. So what we typically do here for recrystallization is we have a saturated solution at an elevated temperature, and then we allow it to cool slowly. As it cools slowly and the crystals grow, they reject impurities. So you get larger crystals and you get more pure crystals. Gases are soluble in water, but their solubility varies. And their solubility has a different relationship with temperature than solids. So when you heat a solution of a solid in a liquid, it tends to be more soluble. The opposite is true with gases. So soda is a solution of carbon dioxide in water, and it's got other stuff as well. And I think we all understand that at a warm temperature, soda goes flat faster than it does at a cold temperature, right? You could try this at home too. Take 2 glasses of soda, put one in the fridge, and leave one out on the countertop, maybe in the sunshine where it's nice and warm, right? Come back a few hours later and taste them. The one that's been out is, yeah, somebody's shaking his head, ew. Yeah, it's going to get flat pretty fast, right? So warm soda goes flat faster. When you pour the soda out of a bottle, the warm soda will fizz up and foam and overflow the cup more likely because it's all the carbon dioxide coming out of solution. When it's cold, it stays in there better. This affects oxygen levels in lakes and rivers. If the water is warm, the oxygen level is lower. At colder temperatures, the oxygen level is higher. And so fish and other aquatic life is accustomed to a particular oxygen level. And so that's why, you buy fish at the pet store. You don't want to put them into water that has a very different temperature because the oxygen levels are very different and they're not going to be very happy. They might even die. Pressure also has a big effect on the solubility of a gas in a liquid. So here we have an illustration of a soda can. What's in here is we've got the soda with dissolved carbon dioxide, and then there's a little bit of space above here, and that is carbon dioxide that's pressurized. When you open the can and it goes psst, right? That's the CO2 pressure coming out. Once that happens, the fizzing begins, and that's the carbon dioxide coming out of solution. You can see this in a 2-liter bottle of soda. You unscrew the lid, and then you see bubbles coming up, right? And it'll just keep doing that until all the bubbles are gone. If we increase the pressure of CO2, what happens is that causes the rate of dissolving to increase. So we have an equilibrium, between carbon dioxide in the gas state and carbon dioxide in the soda. And we have carbon dioxide leaving and carbon dioxide going back in. If we create more pressure by making the volume here smaller, now the concentration of carbon dioxide is greater, and so the rate of dissolving increases. And that will continue until they become equal again. Now we've got more carbon dioxide in the liquid than we had before. The reverse happens when you open the can of soda. You go from this situation and you increase the volume. Now you've opened it to the atmosphere, in fact. And so you have a lower concentration of CO2, and so more will come out than is going in. And it'll keep doing that until it gets flat. We can quantify the effect of pressure on gas solubility. It's called Henry's law. So the solubility of a gas is equal to a constant times the partial pressure of the gas. So this constant, Kh, is the Henry's law constant. It's going to depend on the solvent, the specific gas, and the temperature. And so there's a lot of factors in there. And you just go look that constant up in a table, such as this. So the Henry's law constant for oxygen in water is 1.3 times 10 to the minus third molarity per atmosphere. The solubility is usually in molarity, moles per liter, moles of gas per liter of solution. The partial pressure is usually given in atmospheres. So if we have a high partial pressure of the gas, then we're going to have higher solubility. So the pressurized can of soda, higher pressure of the CO2 means higher solubility of CO2 in the water. So we could do problems like this one. Determine the solubility of oxygen in water at 25 degrees, exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So the solubility of oxygen, we're going to use Henry's law, is going to equal the the Henry's law constant times the partial pressure of the oxygen. So the air is 1 atmosphere of pressure. The partial pressure of oxygen is 0.21. It's the partial pressure of oxygen that's important, not the overall pressure. They used to sell these things on TV that you could put on the can of soda, the bottle of soda. Because some people, I don't have this problem, but some people take a while to drink a 2-liter bottle of soda, right? I've got a problem with soda. I go through it way too fast. And so it would go flat in the refrigerator. So people are trying to, save the soda, right? So there's this thing, and it would pressurize the bottle. You get this little hand pump, and you could pressurize it, and that's supposed to make your soda last longer. The problem is, what you're doing is you're pressurizing it with air. The partial pressure of carbon dioxide in air is very small. And so increasing it a little bit is not going to increase your solubility much at all, and so it didn't really do much good. If you want to save the soda, you need to pump CO2 in there, increase the partial pressure of CO2. And that's what the soda stream machines do, is they use pressurized CO2. So anyway, there's our partial pressure. We need the Henry's law constant, so we're just going to go look it up. So this is for water at 25 degrees. So 1.3 times 10 to the minus third. Kh is 1.3 times 10 to the minus third molarity per atmosphere. It's kind of messy. Yes, you just multiply them. So it's the constant, molarity per atmosphere, times the partial pressure in atmospheres, getting 2.7 times 10 to the minus 4 molar. So 2.7 times 10 to the minus 4 moles of oxygen per liter of solution. Any questions?